With this lecture, we begin the section in Chapter 8 on acid-base disorders. This first lecture will take us up through the calculations of pH and determining arterial blood gases, and then there'll be a second lecture to cover the actual disorders. So first, a little bit of background information and clarification of some terminology. Some of the definitions you see here, some were a little too long to fit on the slide. An acid is really any molecule that readily gives up or disassociates and releases a hydrogen ion. So if they something like hydrochloric acid, which is an HCl, hydrogen and chloride, when put in solution it will disassociate into hydrogen and chloride. That makes it an acid. A base is any ion or molecule that it can accept a hydrogen ion. Bicarbonate, as you'll see in a few moments, is one of those bases because it can combine with hydrogen to give us carbonic acid. We'll see that formula in just a minute. pH is a value used to represent the hydrogen ion concentration. We actually look at it in a reciprocal format. In other words, and I think you can see what I've shown you here, the actual number for the hydrogen ion concentration is actually very small and very difficult number to work with in its pure form. Therefore, we look at pH values, which is a inverse value or the reciprocal of the log. So it's actually taking the negative logarithm of the hydrogen ion concentration in milliequivalents per liter. This will then give us a more usable number. So that's why we see a pH values with 7 being 7 is normally what we would consider in pure pH values is neutral, and then as you drop below 7, the hydrogen ion concentration actually increases. So the smaller the number, the more hydrogens there are, because remember it's an inverse number, and therefore the more acid is present. Likewise, when the number rises above 7.0 in pure science of pH, you move into an alkalotic or basic state, and the concentration of hydrogen ions decreases. Now, that being said, please remember that when we talk about pH in the body and in the calculations we're going to be looking at going forward, when we look at the pH of blood and we look at the normal level of pH, it's actually about 7.35 to 7.45. That's normal blood pH. So we consider that to be our neutral point. So it's not 7.0. Technically, the blood is a little bit on the basic side. 7.35, 7.45 is more basic than it is acidic. But in terms of whether we're going into these disorders that are either acidotic or alkalotic, as soon as you drop below 7.35, below what was in our normal range, we are moving into an acidotic state. Even though the pH is still above 7.0 from a purely scientific standpoint, from a clinical or physiological standpoint, anything below 7.35 is what we would consider acidic for the human body. Again, when we're talking about blood. Okay, and we'll look at that more again, but try and keep that difference in your mind. 7.0 is zero only from or is neutral only from the scientific point, not from the physiological point. And we really are looking at, we measure pH in a number of areas, but blood is the one we're going to look at most commonly. A buffer is any substance that prevents major changes in the pH of body fluids. So a buffer can take something acidic and help bring it back again towards that normal range, 7.35, 7.45 if we're talking about the blood. So it can take something acidic and make it more alkalotic, move it towards the alkalotic range. Likewise, it can take something that's alkalotic if we have something that has a pH causing the blood pH to be 7.7, 7.8. A buffer can help bring it back to a slightly more acidic level. So don't think of a buffer as only something that makes something more basic. It can go either direction. It's returning the pH to normal. Acidosis is the clinical condition in which there is an increase in the hydrogen ion levels above normal. And again, our normal being for the blood 7.35 or 7.45. So it's an increase in hydrogen ion levels above normal or a decrease in bicarbonate levels below normal. In other words, you can be in an acidotic state because of a problem with hydrogen, or you can have a problem with bicarbonate or a base. So if we have problems with either one of those, we can be in an acidotic state. And we'll look at that a little more closely. Technically, acidotic is always an increase in hydrogen ions, but it may be that the hydrogen ions don't change at all. That concentration doesn't directly change, but the amount of buffer, the amount of base changes, so therefore the ratio changes, and suddenly we're in an acidotic state. So try and keep that kind of concept clear in your mind. Acidosis doesn't always mean we specifically added more hydrogen ions, we changed the ratio. And then alkalosis, or alkalotic state, is a clinical condition in which there is a decrease in hydrogen ion levels below normal, or an increase in bicarbonate above normal. Either way, we're talking about a pH really above 7.45. The same kind of concept. We can be adding more bicarbonate, or we can be taking away more hydrogens. Either way, that'll take us to an alkalotic state. All right, so what kind of acids do we have in our body? We can classify acids as volatile or non-volatile. The only truly volatile acid that we have in the body is the weak carbonic acid, and it's volatile because it's actually formed from an equilibrium with carbon dioxide, which is a gas, and that's what makes carbonic acid considered volatile, because it really is linked to the formation with carbon dioxide. So, carbonic acid is extremely difficult to measure because it is in a gaseous state, and it is something that, and we'll be looking at an equation in just a moment, when it's formed it immediately disassociates, and then when it's formed up again it'll disassociate in the opposite direction. In fact, let's just jump for 1 second here to this equation, and I'll come back and explain it a little more, but just so you can see the equation here. H2CO3 is our carbonic acid. This is that volatile gas, and it's really formed, and you see the arrows going in both directions, because, and hopefully you've seen this before also in A&P2. This was something that should have been taught in your respiratory unit. Carbon dioxide, which we get from metabolism, it's our waste product, combines with water to give us carbonic acid. And this is where we said, okay, this combination occurs because of the excess CO2 that's in the body. So that's what makes this a volatile gas. However, as the equation runs from left to right in this case, this quickly disassociates into hydrogen and bicarbonate. HCO3 is your bicarbonate. Likewise, in other areas of the body, this carbonic anhydrase is our enzyme. With the presence of this enzyme, you can actually see bicarbonate and hydrogen join together, form carbonic acid, which then quickly disassociates in this direction. This has to do with the transport of carbon dioxide, and I'll come back to that in a moment. But this is our equation that we spend a lot of time with in terms of calculating pH, understanding acid-base balance in the body. All right, let me come back then to the other acids that we have in the body. Aside from the volatile acid, carbonic acid, all the other acids that we have, and by the way, this one would be regulated via the lungs, because that's how we get rid of carbon dioxide. The non-volatile acids are all eliminated via the kidneys. And so I have some lists of some of those non-volatile acids. There are lots of them. These are the primary ones you tend to come in contact with the most. So if we break down proteins, we'll get hydrochloric acid, sulfuric acid, and phosphoric acid. These are ones that I think you've probably heard of before. They are, again, once they dissociate in liquid, they're going to release hydrogen ions. That's why they're acids. You can also get acid from incomplete, or when we say incomplete glucose metabolism, we're really talking about anaerobic metabolism. If we have low levels of oxygen, we will have, and therefore we cannot move into the mitochondria with the pyruvic acid. That pyruvic acid will convert to lactic acid. This you should already know, but this is one of the acids that can cause a drop in pH or an increase in hydrogen ion concentration. And particularly for those who suffer from diabetes mellitus type 1, what we used to call juvenile onset, those who suffer from that often unable to get the glucose into the cells to break them down, will start breaking down lipids or fats, and in that process keto acids are released. So it's really an incomplete lipid metabolism, and those keto acids can really wreak havoc on the pH balance, dropping it quite low, or again increasing hydrogen ion concentration. We don't have as many bases in the body, but we do have our primary base. It is a weak base, not strongly alkalotic, but it does an excellent job of maintaining the normal pHs in the body, but that would be bicarbonate. Those are our main acids and bases. Our bases, I mentioned that a lot of the acids come from meat sources. A lot of our bases actually do come from fruits and vegetables, more alkaline products that we eat. Not all of them. Some of our fruits are acidic, but a lot of the green leafy vegetables actually provide some more alkaline products and keep our pH in balance that way. All right. This table just gives you an idea of some of the ranges of pH in the body. The only value you have to have memorized is the pH of blood, and hopefully you already know that. These are the ones I just put in here to kind of give you a reference range. Notice the large range of urine. You can go from quite acidic to quite basic, and it's really determined heavily by what you eat. And so depending upon what waste is coming out in the urine will control what that pH is. So it's worth noting that there's a very large range in there. But again, the only ones I want you to have memorized are that for the blood. All right, then we come to this equation. If you'll make sure, if you've not learned this either ever or not learned it well in your AMP2 class, it is important that you understand how we transport carbon dioxide. Remember, it is our primary waste product from metabolism. We've been talking about it a lot in terms of when we were doing the beginning of the course with metabolism. We mentioned the carbon dioxide, but we didn't talk about what we did with it other than to recognize, well, we exhale it. But in order to get it from the cells to the lungs to be exhaled, we must transport it there. So if I'm having metabolism going on in my foot or at the cells in my foot or my stomach or any skeletal muscle, anywhere you want to pick, other than the lungs, I've got to get that carbon dioxide to the lungs, and we transport it in the blood. And we have three main ways, and in your book, page 192 and 193, have some good pictures and demonstrate how that works, how it diffuses into through the wall of the capillary, and for the most part diffuses into the red blood cells, with some of it being dissolved directly in the plasma. A relatively small percentage actually is just dissolved. It's a gas that is dissolved in the liquid of the blood plasma. Some of it moves into the red blood cells to bind directly to hemoglobin, and the formation of bicarbonate in this equation right here that I mentioned earlier, this process happens also inside red blood cells. So the majority of carbon dioxide diffuses all the way into the red blood cell and does one of two things. It either binds directly to hemoglobin. It does not bind in the same place that oxygen binds to hemoglobin. So carbon dioxide does not compete with oxygen for binding sites in hemoglobin. So even as carbon dioxide levels rise, you should still be able, the red blood cell should still be able to handle the amount of oxygen that's necessary to get that to the tissues. So they do not compete with each other, but they both do bind to the hemoglobin molecule. Again, still not as large percentage of the carbon dioxide is doing that. The majority of the carbon dioxide in the body actually forms bicarbonate through this reaction within the red blood cell. Recognizing two things that are always, most cases at least, maybe I shouldn't say always, but in most cases are very abundant in the body. One is water. As long as the patient is not severely dehydrated, this reaction occurs because we are a fluid-based being within the cell. There's fluid in the intracellular, there's fluid extracellular for things to diffuse across. So as long as water is present, carbon dioxide and water will bind together. The other thing that is generally present in more than adequate amounts is the enzyme carbonic anhydrase. This is the most plentiful enzyme in the body. You'll find it in the red blood cells, in cells and skeletal. This reaction is happening in a number of places, including at the kidney, where this reaction occurs heavily to try and balance and move the hydrogen ions out into our urine, into the secretions and into the urine. So this reaction represents the process by which we transport carbon dioxide, the dissolved carbon dioxide, through the blood within the red blood cells, and actually at the kidney this regulation is going on to try and balance really hydrogen ion levels. So important to understand this process and then recognize that this equation is the one we're going to look at to calculate pH, and we actually even use this when we talk about things like arterial blood gases, although we don't calculate often this equation for arterial blood gases. All right, so let's talk about calculating pH. The book does cover this in a very basic sense, so you do have that reference to look back to. What we are actually using to calculate pH is the Henderson-Hasselbalch equation, and the equation is sitting here for you. The red, just ignore that for just a moment. We are looking at a relationship between, really what we're looking at is a relationship between bicarbonate, HCO3 with a negative charge, and carbonic acid, H2CO3. We cannot measure carbonic acid because it is so volatile and it is dissociating very rapidly, but we are capable of measuring carbon dioxide levels, the partial pressure of carbon dioxide in the blood. That is something we can measure from arterial and venous blood. And so because of that, we use that value rather than the carbonic acid, which we have a very difficult time actually measuring. We can therefore, certainly in a clinical setting, you cannot. In a research lab, that's different. But in terms of clinical purposes, that cannot be easily measured. So the equation for pH, which you do have to have memorized, I will ask for it guaranteed on the exam, is you have to know that the pH, this is the value we're looking for, is equal to pK, and pK is a constant. The constant is a number, a chemically based number that gives us a value for the level at which carbon dioxide will dissociate or break apart in water. So you don't have to have chemistry to take this course, so we're not going to go deep into the chemistry of this constant, but you do need to know pK is equal to 6.1. So I need you to know the formula as it is, but then you're also going to have to know this component and a couple others. You'll have to know that the pK is a value of 6.1. And then what we have is it is the log of, this is the value of bicarbonate divided by the value of carbonic acid. So this little slash represents the divided sign, and note it's within the parentheses. So you do this equation first, you find this value first, and then you take the log of that value. Don't take the log of just the bicarbonate. You must recognize you do the actions within the parentheses first. Now I put in red down here carbon dioxide, and it's really the partial pressure of carbon dioxide is the value we actually measure. But the brackets represent concentration. So we're going to substitute the partial pressure of carbon dioxide for carbonic acid when we actually do the equation. Now there's one more tricky part to this. And by the way, the expectation is that you have a calculator to calculate pH using the logarithmic function. So I do not expect you to work out a logarithmic problem on the exam. I expect you to have a calculator that can perform that function. I usually bring a calculator or two with me to class, so if you don't have one, you can borrow mine when you're actually taking the exam. All right, so let's take a look a little further. I said there was one more piece that you needed to know. And so, again, I stuck the carbon dioxide. This is the same equation as on the previous page. I kind of stuck it up in the parentheses. Please still don't confuse yourself and think there's three numbers here. There's just the value of bicarbonate divided by now what we're going to say is the value of carbon dioxide. So this is what my statement says here. Carbonic acid cannot be directly measured, so the concentration of carbon dioxide is used. But it is calculated by measuring the PCO2, or partial pressure of carbon dioxide. So you do this by multiplying it by the solubility coefficient, which is 0.03. So this is an additional value. So we had pK 6.1 up at the beginning of our equation up here. But what you have to do is when carbon dioxide levels are given to you, you must take that value and multiply it by its solubility coefficient, which is 0.03. So whatever value you are given for carbon dioxide, in order to get what was truly the partial pressure of carbon dioxide, you must multiply it by 0.03. Okay? Let's keep looking here. So let's work our way through a couple things. So it's important to also know normal ranges. We're going to use those normal ranges going forward, and especially with arterial blood gases. You don't need the normal to calculate pH, but I want you to be aware of them. Normally, if we were to measure the amount of bicarbonate within the blood, its range would be about 22 to 26. The normal partial pressure of carbon dioxide is 40 milligrams, which is really a range of between 35 and 45. So 40 is right in the middle. The range, everything kind of comes within a range of normal. No one's always precisely at 40, but that normal range is actually 35 to 45. So in order to find that actual value for our equation, you would take 40 times 0.03, and you get a value of 1.2 milliequivalents per liter. So it's important to understand you've got to take that pressure measure and multiply it by 0.03 in order to work it into our equation. So let's work through an equation here where we look at how normal pH is actually determined. So if we take the middle of the two ranges, those are the values I used. Same equation up here, still that red is just reminding you this is the value we're using. So if we looked at our normal bicarbonate level, remember I said the range was 22 to 26, so I'm going to put that normal value at 24. Normal partial pressure of carbon dioxide is 40 with their range between 35 and 40, so I went right smack in the middle. So 24 and 40. So I took that 40 times 0.03 and I got a value of 1.2. Alright, so these are the values that you were given. This is the first part here. So now I've put it in the equation. pH is equal to, remember, pK is 6.1. So I plug that in. Plus the log, and then now here are those two values in the parentheses. 24, which is what I said the HCO3 was, and 1.2, which is really what the partial pressure of carbon dioxide is when I take the 40 millimeters of mercury times 0.03, I got a 1.2. If I put those two values in there and then perform the function, really on my calculator, what I do, for my calculator, I hit the log key, hit a parentheses, then I do 24 divided by 1.2 parentheses, and that will equal 1.3. Let me say that again. This is how my calculator works. I can go into my calculator, and I haven't put the 6.1, I'm just doing this piece of the function here. I hit the log key, then I hit a parentheses key, 24 divided by 1.2 parentheses, and then hit equals, and I get 1.3. Depending upon your calculator, it may require that you first do 24 divided by 1.2. If you take 24 divided by 1.2, you will, oops, I'm sorry. I hit the wrong, I thought I shut off my computer. 24 divided by 1.2, and you will get a value of 20. Then take the log of 20, and you will get 1.3. Okay? So, be certain that you understand how your own calculator works. Because this is the function. If you come to my, you get the calculator I pass out in class, you got to hit the log, the parentheses, 24 divided by 1.2 parentheses equals. That's the cleanest way to do it on my calculator. You can still do 24 divided by 1.2, get 20, and then hit log of 20 and leave out the parentheses. Either way works. It depends upon what you're more comfortable with. I like sometimes to do a math problem where I can just walk straight through the way it's written. Either way, once you get the 1.3, you then add to it 6.1, and you get a pH of 7.4, which is, remember, normal pH is 7.35 to 7.45. So 7.4 is right smack in the middle. I took a normal bicarbonate in the middle of the range, and I took a normal partial pressure carbon dioxide in the middle of the range, making sure that I did that solubility coefficient for carbon dioxide to get that 1.2, and then ran that equation. You'll be expected to do this on the exam. I don't give you normal values of anything. I don't give you the equation. I expect you to write the equation out, and I expect you to make this calculation. Now, there's one other piece I want to point out here. Looking at what we just went through, understand that in a normal pH value, something that ends up being somewhere in the range of 7.35 to 7.45, the relationship between bicarbonate to carbonic acid is a 20-to-1 ratio. 20-to-1 ratio. 20 to 1 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 ratio. 20 to So recognizing this here, if I do 24 to 1.2, remember I divided that, I got 20. That's a 20 to 1 ratio. That's an important thing to understand. If the amount of carbon dioxide increases at the same ratio as the amount of bicarbonate, the pH will not change. Therefore, you will not have an acid-base disorder. So let me try and think your way through that a little bit so that makes some sense to you. Bicarbonate and carbon dioxide, carbonic acid, are in a balance between each other. So as long as they remain in that same balance or ratio, you will not have a disorder of acid-base going on. You may see that you have increased the amount of carbon dioxide, and if you increase carbon dioxide, then this equation back here that we were originally looking at, not the pH, this one, if I increase the amount of carbon dioxide, I'm going to increase the amount of carbonic acid. I'm going to have more acid released into the body because that is the acid. Because that acid, that releases free hydrogen ions. I say, well, it releases bicarbonate too. Correct. But this, anytime there's free bicarbonate, can combine with other things and form more bases. But the free hydrogen ions mean there's more acid present. That's free hydrogens floating around. So when that occurs, that's going to increase the amount of acids in the body. But if the amount of bicarbonate increases equally, then, or if there are other buffers that can help make sure that base level remains the same, you will not have a change in the overall pH. The ratio will remain the same. So kind of think your way through that a little bit. Think about, that's important for when you actually start doing the calculation. Truly, nurses and most clinicians do not find themselves having to do this long equation that they have to have a calculator that can perform the logarithm. So I recognize that. But that being said, what they do is frequently look at what are the partial pressure of carbon dioxide and what are the bicarbonate levels in the blood, and they look at this ratio and can determine what the pH is within. Is it still going to be within normal? Is it going to be more acidic or more alkalotic? They may not have a precise number that they took the time to calculate, but they can recognize this ratio that exists. We take you through the full calculation to help prepare you for the idea that you still have to understand the concept behind it, and particularly this ratio that exists. All right, let's take a look. One more calculation real quick here. This is an abnormal value. So in this case, I give you a bicarbonate level of 30 and a partial pressure carbon dioxide of 18. Let's jump back here. Remember what your normal range is. Bicarbonate is 22 to 26. So if we're at 30, that bicarbonate level is high. Likewise, carbon dioxide range is 35 to 45. Partial pressure carbon dioxide at 18 is low. This is an important thing to think about right here. We're going to look at it again with arterial blood gases. If bicarbonate is high, we got to be starting to think, ooh, that's more base. That's probably something alkalotic going on. If carbon dioxide level is low, if carbon dioxide in our equation back here, keep bouncing back and forth. Oops, sorry, I'm going the wrong way. If we are saying that carbon dioxide causes the release of free hydrogen ions, then less carbon dioxide, lower than the normal range, will be less hydrogen ions released. So that in fact, sorry, I keep bouncing around on you guys. The 18 millimeter mercury partial pressure carbon dioxide is very low, which means very low hydrogen ion release. This is actually leading us to a more alkalotic state as well. So take a look at how that works. 18 times, again, so you should have kind of thought that before you even did the calculation. That's high. If I know the normal range, that's high. That's thinking alkalotic. That's low. That's less acid available then. That's probably more alkalotic as well. If I do the 18 times 0.03, I get 0.54. My calculation is the log of 30 divided by 0.54, which gives me a 1.74. If I add that to 6.1, I get a very high pH, a 7.84. This is a dangerously high pH. Given the fact that we had said earlier that the body contains a lot of acids, hydrochloric acid, phosphoric, sulfuric acid, lactic acids, lots of acids present in the body, we can handle a lower pH. The body can maintain that pretty well. But when pH gets high, 7.84, alkalotic states are actually more damaging, more caustic to the body than acidotic states. So this is a very severe problem. Someone's got a pH of 7.84. All right, so we will work through one of those, or maybe a couple of those problems in class, time permitting. That is the intention, at least, to work through the Henderson-Hasselbalch equation, so you have an understanding and can for sure do that calculation, know how your calculator works. That's one other thing to kind of talk about before we move into arterial blood gases is the idea of the chemical buffers, the buffers that we have in the body that can help us to balance our pH. These buffers, again, their job is to bring pH back to normal. So I've just listed several of the buffers here. I don't need you to go in much detail. The book has quite a bit of information on them. Scan it. Don't read it trying to memorize or get a lot of intensity out of it. But taking a look here, here's a bicarbonate buffer system. And this is actually sodium bicarbonate. So oftentimes bicarbonate isn't by itself. It binds to something else. In this case, sodium. So if we have increases in hydrochloric acid, it can bind to sodium bicarbonate. That just gives us some carbonic acid and water, which again, this can then disassociate again as well. Remember, we've looked at what that can do. So this is one of the buffer systems. We have already the hydrogen-potassium transcellular exchange. We've talked about that with regards to the potassium levels in the body. So anytime you have a more acidotic state, expect there to be a problem with potassium levels, because if the hydrogen ion concentrations go up, especially if it happens rapidly and you have more hydrogen ions, the body will work to buffer that by switching out potassium. That can lead to hyperkalemia when you have potassium working itself into the extracellular fluid. And this is taking place at red blood cells, liver, muscle cells, and definitely this exchange also occurs at the kidneys. So there's always a risk with acid. Whenever you think about an acidotic, alkalotic state, hydrogen ion issues, think about its effect on potassium levels. Body proteins are great buffers because they can either bind to or release hydrogen, and even the bone plays a role in binding to hydrogen and works along with potassium and sodium with regards to that binding and buffering process. So these are just some of the buffers that exist in the body. Again, sometimes I ask you just to, can you define a buffer? Can you just list one or two of the buffers? I very rarely ask for any kind of lengthy exchange, or a description rather. The one most important one really and truly is this hydrogen and potassium exchange, but we've already actually talked about that already with potassium. So it's fair game to talk about again here as a buffering system. So be aware that's probably the most important one. The others more just recognize that they exist. Then how we actually regulate our pH. There are two ways in which we regulate it: through the respiratory system, and that's where we're actually dealing with getting rid of carbon dioxide or holding on to carbon dioxide depending upon what we need. And the renal system, the kidneys, primarily work on getting rid of or keeping more of the bicarbonate. We also work, the kidneys are also excellent at getting rid of excess hydrogen ions. So the kidneys are really your long-term, probably your better control of acid-base balance. They have much longer effects, but respiratory control is rapid. If I want to change my pH very quickly, I can change breathing patterns consciously, or even or even through the control of the medulla oblongata, I can change my respiratory rate to fix pH. But it's usually short-term, rapid fix, but it does not last. You usually cannot be, for instance, in a hyperventilative state for very long, and then the body goes back to normal. Kidneys take a little longer to get themselves going and really get that regulation in place, but once they do it, they can maintain it for you for years. So those are the two systems that control our pH, and we'll talk more about them with the disorders. And then finally, we have arterial blood gases. So in arterial blood gases, we're looking at a process by which we can measure the health of the pH in the body. We can look at what our lungs are doing. We can get a sense of what's happening with bicarbonate levels, and therefore a sense of what's happening with our kidneys. So it's a good clinically based test. The book does mention the arterial blood gases. It's in the same section when they talk about the anion gap, which was mentioned with the chloride lecture. So it's another one of those laboratory or clinical tests that can be done. I want you to be able to interpret an arterial blood gas. So that's what we're going to take a look at here. So in interpreting an arterial blood gas, I give you a table, and there's some sheets attached to the Moodle page that also list the tables, give you something to read through on this process. But I'm just going to give you this example right here. There's really a step-by-step process to work through. I'm not a huge stickler on whether or not you know the steps in order, rather just that you address each of the steps, whether you put them all in order again or not. There's really 6 steps, with a 7th step being the final diagnosis. It's really not a step, it's where I ask for that final diagnosis. And so this actual arterial blood gas process is part of your exam. You get a table, you'll get a place to put the steps. So just so you're aware, this is something that it winds up being about 14 to 16 points on your exam. So what will happen is you'll receive a table, and in the table I will give you you have pH, partial pressure of carbon dioxide, oxygen saturation, and bicarbonate. These are the values that are given there. Now, we've not talked much at all about partial pressure of oxygen or oxygen saturation. For those values, I will actually give you the normal values for those. I expect you to know normal pH value. I expect you to know partial pressure of carbon dioxide, and I expect you to know the levels for bicarbonate. Those were that 22 to 26 and 35 to 45 I'd given you already, and then obviously pH is 7.35 to 7.45. I will provide you normal levels for oxygen saturation and partial pressure of oxygen. They're part of the arterial blood gas, but they figure a little more into the respiratory chapter than they do right here, so I don't want to go into depth on that at all. I'm going to just kind of have you take my face value. I'll give you a range. If it meets the range, it's normal. If it's below the range, it's low. We're looking at really oxygen in the blood with that. But in terms of pH, we're not really focused on those oxygen levels. It's just another aspect of this test. So you'll get a table that will have, in the center column, it will have the values for each of those, and then these will be blank. And here's what you do with the steps. You take a look at the pH. It's 7.30. That pH is below normal pH of 7.35 to 7.45, so we say that pH is acidotic. Then you look at, well, what's the partial pressure of carbon dioxide? It's 58. The normal range is 35 to 45, so this is high. So notice step 2, the carbon dioxide level is acidotic. It's high. And when the carbon dioxide levels are high, that means more hydrogens are going to be released, so that means there's more acid, so it's acidotic. Again, I'll give you normal values for these, but a value of partial pressure of oxygen of 50 is very low, so that we just list low. And an O2 saturation at 80% is also very low, so we list that as low. The bicarbonate level is at 26. 22 to 26 is the normal bicarbonate level, so we just list that as normal. So steps 1, 2, and 3 address pH, carbon dioxide, and bicarbonate. All right, so then once we've got those 3, pH is acidotic, the CO2 is acidotic, and the bicarbonate HCO3 is normal. Step 4 says, okay, looking back at those first 3 steps, which of the steps match? Which one are both acidotic or both alkalotic? And so we look and we see that the carbon dioxide level is acidotic and the pH is acidotic. Therefore, when we look at that, we can say those 2 match. When we look at something like that and say, okay, the problem's with carbon dioxide, then we say that's a respiratory problem. We know it's acidosis because it's acidotic. And if it's a CO2 issue, then it's in the lungs and it's respiratory acidosis. If the problem had been with the kidneys and the kidneys had acidotic, then we would say that was metabolic or a kidney problem. So renal acidosis, we use the term metabolic for renal. All right, once we've looked at that, then we go look at the other things. So which one's matched and which one is opposite. So or not matching. So we say, okay, well, step 5, the bicarbonate is normal. So it's not trying to make up for it and going in the opposite direction. It's not alkalotic, because that would be a non-match alkalotic. But what we can say is, okay, the kidneys aren't trying to compensate for this problem. They're not trying to make it better. It's still in the normal range. So the kidney's not fixing it yet, at least not yet. All right? Again, the step 6 asks you to address this oxygen level. and so they're low. And when things are low, even if only one of them is low, that's hypoxemia. Hypoxemia is low oxygen in the blood. So even if one is low and one is normal, we call it a hypoxemia. Both are low, we still call it hypoxemia. So that's the arterial blood gas. That's the end of that. That's going to be the end of the lecture. I encourage you to please take the time to look at the information that's posted on the Moodle page that walks you through the steps for filling out a table of arterial blood gas, and we'll work out some of these in class as well.